Welcome to the next lecture in the series Quantitative Methods in Chemistry. In the last class, we were able to see how using MATLAB we could simulate curves that are just not linear curves but also something slightly complicated like the Michaelis Menten curve. And we also realized that once the curve has been simulated, we have a better way of guessing whether we are sampling the right concentrations for a given Km and Kcat. This helps because if you are trying to mutate a protein for a certain function, let's say that the function is not supposed to get altered, then one can carefully make sure the concentrations of substrates are made in such a way that this can be done. So now going to the next step, once you have collected the data, we have to fit it in order to redetermine what is Km and Kcat. Let's repeat the simulation that we did in the last class, where I have a bunch of substrate concentrations, and these were simulated with 3 different Kms and Kcats for chymotrypsin, pepsin and tRNA synthetase respectively. And what did we see? Let's resimulate it. We see 3 different colors here, one for chymotrypsin in blue, the pepsin in red, and in orange the tRNA synthetase. Now that we have obtained this is just a simulation. Let's now forget the fact that we have simulated this data. Let's try to take the final one, the tRNA synthetase data. Let's try to plot it, plot S, and then we can actually say velocity. So you get this curve that we have just simulated a few minutes back, right? Now remember, the line here is not a fit, it is just joining the dots, the data points that have been acquired. Now if one has to determine what is the Km and Kcat, this has to be fit to the Michaelis Menten equation. And as we saw in the last class, it is very tempting to invert this, that is take 1 over the velocity and plot it as 1 over the substrate concentration, which helps us get the Km or Kcat from the slope and the intercept, and therefore one can determine what is this Km and Kcat. This is not a good way of doing it, as I had mentioned earlier, because the error that comes in the velocity of the reaction is not going to be same when you are going to invert it and plot and extract the information out of it. We will still do it just for the sake of completeness, so that we understand how initial guesses for a certain fit can be used in order for this purpose. Okay, so now that we see these are the data points, we will be starting a tool called Curve Fit Tool, CFTOL, gives you this graphical user interface which can help us plot any type of curve and fit it to the equation of our interest. So the X data here will be the substrate concentration, and the Y data here is the velocity of the reaction, basically the rate of the reaction. And what you are able to see here is that the black dots indicate the data points and the blue is the fit. Of course, it is fitting with an equation that is polynomial with the first degree, basically a linear equation as seen here. And as you are able to adjust, the R square is extremely poor, and more importantly you are able to see none of the data points pass through the fitted curve. So this indicates that it is a poor fit and we need to find something better. And since we know this is not going to be a simple polynomial equation, we can go to custom equation and rewrite the equation. The equation that we need to write is K times X, where X is the substrate concentration, divided by Km plus S, X, right? Why am I not writing S here? Because the variable here is X. You can always change it to capital S and write the same thing. And what you are able to see here is that this is having a problem, largely because the Y axis is having a 10 power minus 6 term and it is unable to fit this. If you recollect the equation that we are trying to use, we have velocity is equal to Kcat times E naught times the substrate concentration, the whole divided by Km plus S. And we know for a fact that we are taking the substrate concentration as a known amount. In this case we used for 10 micromolar concentration of the enzyme, and then we simulated these curves. And important thing one has to understand is that this K here has that information that goes in. So one thing that a person can do is to actually change the velocity. So let's call it a new variable. So we can call it test underscore velocity is equal to velocity divided by E naught. So now that we have gotten it, we can actually recall the curve fitting tool, and now you get an equation that takes care of the enzyme concentration. This is important because if the same enzyme is prepared in multiple batches again and again, and when somebody wants to determine what is their Km, Kcat, the fits here would be independent of the concentration of the enzyme employed. So this helps in comparing things across. So here once again you are seeing a problem that comes up where it's not able to determine the proper fit. All right. So now when I change the fit options, the fit options give you what is the start point of the fit, what is the lower level and what is the upper level of the fit, and you can always set the lower level to 0 because you are not going to have Km or Kcat that is negative. So this helps the fitting algorithm go faster, and for some extremely weird reason it is also trying to fit for substrate concentrations that are negative, which do not make sense physically. So therefore let us choose to ignore the part of fitting that comes for concentrations that are negative. And what you are able to nicely see here is that the fitting that is in the blue curve is nicely passing through every data point. And since this is the third simulation that was done for tRNA synthetase, you are able to realize that the Km that was used, which is 9e minus 4, that is 9 10 power minus 4, is exactly what it fits out. You are able to see that the fit is 0.0009, and the value of Kcat, which is given as K here, is nicely coming as 7.6. And as you might remember from the previous lectures, you also would like to know not just the average value but also the standard deviations that go with these measurements, and you are able to see that the coefficients are predicted with a 95% confidence bounds as shown in the numbers in these brackets. It is not surprising that these numbers are exactly that of the number that comes up as an average, because we have simulated this curve with no error that goes with any of these measurements. The same is the case for Kcat, where Kcat is reliably determined. Previously, when you did not divide the velocity of the reaction with the enzyme concentration, the problem was the fit was trying to get the product of E0 to Kcat, and what ends up happening is that you are able to realize is that Kcat is like 7.6 units, but E0 is something like 10 power minus 6 units, right? So this could actually have a problem here. One has to be careful to check whether we are doing all the fits the right way. Yeah, I have divided it by E0, not by 10 power 6, so that makes sense. So one has to be careful when you are having a fit that is a product of two different numbers that you are trying to figure out, and if one of that number is already known, it is a smart choice for us to actually divide the rate with that parameter. In this case, that is the enzyme concentration, right? So now that we have seen this, we will try to see how the 1 over velocity when plotted with 1 over substrate concentration might help us get this. In order to do that, let us recollect ourselves what is the equation that is involved. So we have velocity is equal to Kcat times E0 times substrate concentration divided by Km plus S. This is the Michaelis Menten equation. Of course, what we have done here is to take the E0 to the denominator, so that makes it velocity divided by E0 as a function of S is what we just plotted to get Kcat and capital Km. So now what we are trying to say is that let us say we take the reciprocal of this, it is going to be E0 by VL, that is going to be equal to Km over Kcat times 1 over S, the substrate concentration, plus 1 over Kcat. So what we are able to realize is that we will get the slope of this fit as Km over Kcat, while the intercept will be 1 over Kcat. So if we are able to take, if you are able to divide the slope over the intercept, one will get Km, slope by intercept will give you Km. On the other hand, you will also get 1 over intercept as Kcat, right? So why don't we take a look at how this can be done. So we can say test val inverse is equal to 1 over test val, okay. And then we also need to have S inverse, so we are going to say S inverse is equal to 1 over dot S. Then let us go back to the curve fitting tool, and then here we can actually add another fit which will be S inverse, that is in the x axis. On the y axis you want test underscore well underscore inverse. So now you do this, what you are able to see already is that once again MATLAB is in a hurry. It's taking all the data points, you are able to see multiple data points here, here and here, and it's fitting it with a polynomial, with a first degree polynomial. But let us not do that. What we can do is to write our own custom equation such that it's m star x plus c, and then you say fit. Of course the fit options here might not be that required because it's able to nicely fit, the r square comes as 1 because we have simulated this data. And what you are able to see here, that the intercept is 0.1316. So what is 1 over the intercept? You are able to see that it comes up as 7.5988, which is 7.6 that we have simulated. Then if you would like to know what is the other one, the way you do it is that you take the intercept, which is 0.001184 divided by 0.1316, and you are able to realize you are able to get 9 e power minus 4, which is what you ended up using. And the important thing one has to note is that although the values come up similar, the moment error starts to play a role, you will realize that these could end up being different. That is what will be the focus of this current class. So let us go back here. So I have written another code to perform the same. So let us take similar type of concentration that we would like to work with for the enzyme, and this time we are taking the chymotrypsin example. So what is going to end up happening is that we are able to understand, and in the initial portion of the lecture also we were telling that repeats matter. One has to repeat the experiment a number of times. We will understand many different aspects from this simulation, how repeats help you understand what kind of values come and how do they help in determining the precision better. As always, we start with clearing the screen, clearing any variables that might have existed, and clearing closing all the figures that might be present. And these are the set of values that we end up using for concentration of the substrate. And then we are going to repeat this experiment 10 times. Let us start with 2-time repetition. And here once again we are using enzyme concentration as 1 e power minus 6, that is 1 micromolar, and molarity is the concentration that we are trying to use. If you might remember the initial lectures where we were trying to understand the Gaussian distribution, basically the normal distribution, we used this kind of function called make dist. We are trying to do the same thing, where this time we are trying to noise correct the Michaelis Menten constant, that is Km and Kcat, with their average values. We are still using the same average value that has been used for chymotrypsin earlier. Let us see what was used, 0.15, 0.015 sorry, 0.015 and 0.14. So we are still using the same value, but what we are trying to say is that we are trying to say for Km the third decimal has an error or uncertainty associated, and it's simulated as a normal distribution. On the other hand, for Kcat also we are assuming the same value, but we are assuming the second decimal here has an error. So what you are able to realize is that the error propagation is nicely taken care by this, where we will be assuming random error for each of this variable. So basically both Km and Kcat vary randomly and are not correlated with each other. You can also make them correlated, but let us not worry about such a case right now. We can assume that purely Km and Kcat can be randomly varied, and then we are repeating the simulation the same way, just that here j goes from 1 to the number of repeats. Let us say you are repeating this experiment 2 times. Now this protocol will be repeated twice, where the rate of this reaction is calculated as E naught star random value of Kcat. So basically what it does is that now let's try to understand what is this random distribution. Let's say let's clear any variables that exist. Let's say x is equal to make dist, and then we can say normal. That means it's a Gaussian distribution. Let's keep it at 0, and we can say 0.1 is the standard deviation associated with it. So then we say random x, what MATLAB does is to randomly pick a value with an average of 0 and a standard deviation of 0.1 across many such numbers. So you can keep repeating this random x and you are able to realize that the value is coming quite different each of the time you are simulating. So this is a nice way to simulate a normal distribution of error for a given average value of the variable that you are trying to look at. So whenever I call random x, it's picking a certain value. So if you are able to realize here, the random value of k cat is picked and the random value of km is picked, and these two are very different processes. When you repeat the same random x multiple times, you don't even see the numbers coming up similar, but if you repeat it enough, if you take the average and the standard deviation, you will finally converge at the values that we have given in this case, which is 0 and 0.1. So similarly is the case with km and k cat, where you have a certain average and a standard deviation that has been given, and it is simulated with a normal or a Gaussian distribution. So what ends up happening now, the velocity is now simulated for every substrate concentration, and the enzyme concentration is kept constant. You can also introduce an error there, that could also be done, and the random value for each km and k cat will simulate a certain specific value of rate. And as the concentration of S is increased, the k cat is also randomized, so is km. So therefore you are going to randomly determine the rate, and then of course as we did the last time, we are also trying to get the rate saved for all these repeats, so that we have a memory of how many repeats went through, and that goes finally into the value rate. We can always change this rate into cumulative, so that we understand what this variable is. And next step, what I am trying to do is to divide the cumulative rate with the enzyme concentration, so as to normalize the plots that might end up coming, so that finally when you fit out, you just determine km and k cat, and you would not have the problem of fitting the concentration of the enzyme as well. Then the next step, what I am trying to do is that for the length of S, meaning that how many ever times the repeats have happened, I am trying to get the average of the cumulative rate. So basically this cumulative rate right now will be a 2 by 11 matrix, because you are having 2 repeats and 11 concentrations of substrate, maybe even more since I added a few, and now it will find the average for these 2 repeats. When you are doing 10 times, this will be a 10 by n, where n is the number of substrate concentration, it will be a 10 by n matrix, and now it can determine what is the average and the standard deviation in each of these separate steps. And then what I am trying to do is to plot the error bar. So let me not fit this curve for now, so that we understand how we can fit it ourselves using the curve fit tool. So all I am doing is to plot this figure. So let's see how it looks. So there you go. So what you are able to realize is that as a function of substrate concentration, you have measured the rate normalized to the concentration of the enzyme, and you are nicely able to see the every data point has its own random error that comes. This is not a constant error or a propagating error, where as you keep increasing the concentration, that error increases. That is not happening here, because the highest of concentration has lowest error, and something in the middle has a lesser error than the one that was previous and the next point. So this indicates that there is no correlation between the error that comes, because we have randomly simulated km and k cat. So now let's go to the next step and try to use the curve fit tool. We can erase any of the previous fits, or we can still continue to have them. So in this case, S is the substrate concentration, and you want something like the average rate to fit. So what you are able to see, you do not see the error bars here. All you are able to see is only the average values. So we go back here and then say custom equation. So the custom equation, what do we end up writing? K star x k star x divided by km plus x. All right. So now what you are able to see, in comparison to whatever fits we got the previous time, where there were no errors involved, in this case you are able to realize the fit almost passes through all the data points, but some of the data points are above and below. Of course, the moment you start introducing the error into this, you will be able to understand, yes, the fit does satisfy the data better. We will be fitting this and showing the plot simultaneously in a moment, but let's take a look at what values ended up coming. So in this case what is happening is that for 2 repeats that you perform, the Km, although you simulated Km with 0.015 as its average value, the average value ends up coming as 0.0127, which is less than the value that you simulated, and the 95% confidence interval, that is within 2 standard deviation on either side, goes from 0.01065 to 0.01475. So what you are able to realize is that this value is slightly far away from what you simulated, and that comes up because of the error that came up in Km and Kcat. Let's take a look at what was Km. Km we provided as 0.14, and you are getting something like 0.1364. And the range between 0.1324 to 0.1404, and this is quite interesting because you nicely gave an average and standard deviation here. So one would assume that, or one would anticipate that the average of this Km and Kcat come very close to wherever you anticipated, and the error nicely represented. This is not happening largely because the number of repeats that you have done is extremely low. Why don't we repeat the same thing, and instead of doing it for just 2 times, why don't we do it 10 times? So now you are able to see nicely the errors and all the other values are also coming into play. So let's go ahead and fit it again. Alright, so now what ends up happening is that for 10 repeats that you ended up doing, you are able to realize that the Km is coming very close to the Km that was provided, and probably the error does end up happening in the in that decimal. So basically it goes from 0.0146 to 0.0169. So you are able to realize that the lack of confidence comes in the third decimal in this case, which is what you ended up simulating. If you have even more number of simulations, this might get better. We will take a look at that in a moment, and nicely the Kcat average comes up to the value that you ended up giving, and in fact the error probably is in that decimal that you have provided in the second decimal. If you realize 0.1385 is 0.139 and 0.142 is 0.142. So you are able to realize that the error comes in the third decimal. So this once again illustrates the fact that the more number of repeats that you are able to perform, you would be able to get an analysis of the error that goes nicer. And one important fact one has to realize is that in this case the fit almost passes through every data point that one is able to get. Only a few data points are farther away. In order to exemplify this, why don't we repeat this again? So we are repeating with two sets of repeats, and then let's get average rate again, and you are able to realize that some of the deviations that come, so even the R square might be nice and indicative of the same, but you are able to see visually how many points go farther. So now wantedly, for the sake of understanding this better, we will simulate it so many number of times that now the fit will also come up beautiful. So you are able to realize as the number of repeats start to get better, the fit nicely goes through the average values. Almost only this data point is slightly off, but that is not a big deal, and you are able to realize that the confidence intervals, the range of values that comes after fitting reduces significantly. Same is the case with Kcat, and of course your R square is increasing, but be a little careful about the R square. We will take a look in a moment what happens there. Why don't we repeat the same process that we did earlier of doing the 1 over S plot? So how would we do it? We will say S in is equal to 1 over dot capital S, and then we have a cumulative rate. Actually we have the average rate that we would like to do. So average rate inverse is equal to 1 over, do we take it, 1 over average So now let's go back and fit it. This is a third fit. Remember we have had 100 such data points. It's going to look pretty reasonable, and you are able to realize that the intercept, which is P2, comes up as, we can actually go back, write our own equations. That's a good practice. Write a custom equation of m star x plus c. This is y equal to mx plus c, the standard plots that we have, and the intercept is 7.898. So we have to take the inverse of that. So what is 7.898? That's 0.1266 Oh wow, so you're able to realize there is a difference that comes in kcat. You wanted a kcat of 0.14, the error in the slope or the intercept is significant. You're able to see the error in the slope goes from 6.943, why don't we invert that and see that, 6.943, so that's 0.144 and 1 over 9.303. So you're able to realize, although you did 100 simulations, when you are inverting the plot to get the fits, although the fit is fantastic, you are able to realize your kcat goes from 0.10 to 0.144. So this indicates the fact that although your fit is great, although it's easy to fit linear curves, you are able to realize that when you take a reciprocal of the model, the noise seems to be corrupting the data when you are getting it back. So this is an important inference that one has to have in mind. Why don't we take a look at what happens for Km. So Km is determined by getting 0.1051 divided by 7.898. And what do we get? It comes up as 0.133, and of course remember you also have a range that goes here. Now the question comes, are you going to be dividing this with this value, this with that value? So once one starts to understand, the error that goes in the slope and the intercept is going to propagate and result in more error in the Km determination. So I leave it to you guys to determine how this can be propagated and measured, what goes on when you are mixing and matching different values. So one has to be very careful when a data is obtained and one fits, and in this case we are able to realize that even with 100 repeats this is a problem. Why don't we repeat the same linear plot with just 2 repeats? We can generate this the same way, and then let's try to fit this average rate, and here you are able to realize that it starts to go much farther away, and the range of this intercept that we got previously, we got somewhere between 6 and 9, now we are getting between 4 and 13, so it starts to get extremely poor. Even M, the slope was better determined the previous time with 100 repeats, now it's getting worse. So I hope this makes you understand it's not a great idea, if you know the model precisely, it's not a great idea to invert it, to linearize a plot and get your final values. It's better to use them as it is to find the actual errors that propagate. Now that we have determined this, why don't we take a look at how a simulation can be done in a single way and the fitted values come up in a single plot. Once again, I am showing it in the value of simulation. Hopefully in the later week we can try to do an experiment, get an experimental data and fit it, and go forward with that fitting in MATLAB itself. So now what we can do is to have the same 2 repeats, and the code that I had ended up muting, right now I will erase the if statements. The same thing that we ended up doing in the curve fit tool can be done in terms of command prompt as well. So I would like to show how MATLAB could be used for us to even write codes, although we are not knowledgeable in generating the codes. For instance, let's say you have this code that you ended up fitting the average rate. What one could do is that one can actually go to this file menu up here and then say generate code. The moment you click this, what MATLAB does nicely for you is that it nicely generates the code of how this fit has been performed with the different variables that you ended up providing. If you remember, what did we do? We took x data as a substrate concentration and y data as the test underscore velocity, which we ended up simulating, and once you get it, and we fitted this equation with the fit type of k star x divided by km plus x, where the independent variable is x and the dependent variable is y. This is where I said if you would like to use the independent variable as capital S, you can do the same thing. You can remove the x here and make it capital X, where you determine what is this x. And the algorithm that is used and the fit options that one ends up using can also be mentioned here, and if you realize all these were present in the fit options here. You can change it in the graphical user interface, but when you are having a large set of data set to handle, let's say the same Michaelis Menten curve is done for 10 different enzymes at multiple different concentration at very different temperatures to determine other thermodynamic parameters, then one might start to actually write scripts such that the data is read from the Excel sheet as I had shown earlier, and then MATLAB used towards such fitting. So the same thing that we ended up using here is in fact can be written as a code. So if you see here, the method that is used here is non-linear least squares fit, and the algorithm that's used here can be changed to Levenberg-Marquardt. These are different algorithms. I am not going to go into the details of it. I am sure if you research a little bit, you will be able to understand what is the difference between trust region algorithm versus the Levenberg-Marquardt, and then whether to display the data points and I mean what are the lower limits. So basically we can end up changing the lower limits so that the fits can start wherever it is. Now coming back to the fact, where could the linearized fits could be useful, basically where can the 1 over s and 1 over velocity fits could be useful is that you can give reliable starting points. If you, many times these kind of fits, here we are only fitting 2 variables, but you could be dealing with equations that have multiple variables that go into them. So in such a case, what ends up happening is that it will be a good idea to have a reasonable guess of where your starting point should be, as we are giving here. Okay, the starting point would help you end up converging the fits faster. Remember, although all these are done by computers, these are indeed memory intensive. So at times where if you are able to bias it carefully, then one can give the starting points and the lower and upper limits within safe constraints. For instance, in this case you know for a fact that the Km and Kcat cannot have values that are less than 0. So in which case what one could do is to say set the lower limits to a certain number. Let's say that you have mutated chymotrypsin to change the kinetics, and if you know for a fact you are not going to have reaction rate that is much higher than that of the natural enzyme, then you can put the higher bounds also to whatever is already known in the literature. Of course, you can go, let's say 10 times more, but any value less than that was what is going to be probed. So what you are able to realize, for 2 variables you need to set multiple parameters such as the start point, the lower limit and the upper limit. All these could be educated guesses so as to make sure your convergence goes much faster. And these are the fit parameters that you ended up providing in the script, and what you are trying to say is that go ahead, fit it for me and give me something called the goodness of the fit. So basically the 95% confidence intervals, 98% confidence interval are all stored in this variable called goodness of fit. And then what is it trying to do? It's trying to say, okay, after you have done that, plot the fit result to the x and y data set that we have done. So if you run this, of course you need to save the fit. Oh, it's having an error, I'm not sure. Okay, that's because we have rewritten the test underscore velocity, but we will be taking a look at it in a moment, where you will be able to see that the plot of the fit to that the x and y data that we have provided is nicely done, and the legend is provided. And where should the legend be kept? So basically it's kept in the northeast top right corner of this. And what is the x label, what is the y label, whether to keep the grid on, and how to prepare the curve. So all these comes up so as to, oh, it actually generated the fit for all the 4 fits. So what ended up happening is that since we have 4 fits here, it ended up creating the script for all of them. So what one could do is that instead of doing this, after you prepare the fits for one of them, you could generate the code, understand how the code goes, and you can also write a loop such that if you have 10 data sets, it can loop through the number of data sets, make the fits, and finally give you the values. So that is what we are going to be taking a look at, and this is the script that I have given. So what I am trying to do, we are once again using the same equation, keeping the same substrate concentration. So we can have any number of repeats. Let's say we have 10 repeats, and then enzyme concentration is kept at 1 micromolar. We are keeping the same values that we have used for chymotrypsin for Km and Kcat, and we are repeating it several times so that velocity gets determined 10 times. The accumulated rate is saved within that, and the average and the standard deviation from the accumulated rate is used towards showing an error bar fit of concentration of the enzyme to the average and the standard deviation. After having done that, the next thing that we do is to prepare the curve of S and S in the x-axis and the average rate in the y-axis, and then fit it with the Michaelis Menten curve as I had shown earlier with the start point and all that. We can actually keep the start point to 0, 0 in this case. I have also generated the code from MATLAB, so it picked up from something like that, and then the goodness of fit is given here. And now I am also determining what is the range of answers I got, and I am saving it in this a variable called range underscore out. Okay, and then I am plotting the figure with fit result. If you remember, I had already plotted it with the error bar, and then now we will be plotting it with the fitted result. So let's once again keep this portion of the fitting off so that we can see what is that we end up getting. So let's run this. So what you are able to realize is that the average and the standard deviation are nicely provided. Just to exemplify the point, if you only do 2 repeats, you will realize that the error is quite haphazard. You are able to realize that the error across different measurements is quite variable because you just did 2 measurements. Remember the concepts that we introduced of the sample and the population. If the sample is a very small subset of the population, you might not properly represent the average mean average of the population with the mean of the sample. So it's always a good idea to have good number of repeats. So we get something like this. As you increase the number of repeats, the error bar will slightly look very reasonable across all the points that we get. And remember, once again, we are simulating here. In reality, you would be performing the experiments to get the error values. Okay, now that we have seen this, why don't we see how the fit also works out. Okay, so now what we end up doing is to run this where the starting point is slightly changed. Instead of 0, 0, which results in an error, I just put it to a very small value. You can add more zeros so that you ensure that you get the right km kcat and there is no bias. And what ends up happening is that the same thing that I ended up writing in the script, it's able to plot the data points. So let's take a look at it. It's able to plot the average velocity as a function of substrate concentration, and it's showing the fit in the blue line with the data points with the blue circle and the error that goes with each of them. So one has to understand here, the fit that comes up has to pass through most of the data points. And if you remembered when I showed the CF tool, you realize that the fit did not pass through each of the point but was very close to it. And here one is able to understand that the error that's associated with each of the measurement, if you see this data point, what ends up happening is that, let me zoom in a bit so that you can see it better. What ends up happening, although the fitted curve does not pass through the data point, you are able to realize within 2 standard deviations it gets very close, within 3 standard deviations it's going to fall. Once again, this helps you understand what does precision mean. Apart from that data point, if you are able to take a close look, all of them fall very nicely within the fitted curve. So we can repeat it again and again. You realize that now when we repeat it for the second time, unlike the last time, this time all the data points and the errors nicely fall. So this clearly illustrates the effect. Last time this was the data point that was problematic. So this clearly illustrates the effect that when a person repeats the experiment multiple times, the true value does come out in the average and standard deviation, and that's why repeats matter a lot. Okay, so now that we have understood this, the same way fitting can actually be changed to other parameters as well. So if you want very high 3 standard deviations, you would be able to get these values also. And one thing that I am able to do here is that if you pay close attention to the legend that I end up plotting, I am able to get the km and kcat values as well with the average and standard deviation. So one can actually fit curves at a much faster rate by doing this than by using a graphical user interface. So let's recollect and think about what has happened so far. Remember, I actually did not go through the step of how the initial rate is determined for each of this substrate concentration. So one of the examples that we could try working out as an assignment for this week could be where the rate is given for every substrate concentration for a given amount of enzyme, and we can get the initial rate. After you get the initial rate, you can try to plot the velocity normalized to the enzyme concentration as a function of substrate concentration, fit kcat and km, and get these values. Therefore, you finally end up seeking the true value that you would like to measure. So I hope these set of lectures this week have made you understand that using a computational tool like MATLAB would help you simulate some data, simulate functions that you might not be very comfortable with to start, but then as you start simulating them more and more, as you start repeating them, you understand which variable is sensitive to the parameter that you end up measuring. And at the same time, you get a complete hold of which are variables can vary and which would end up determining the final fate of what you end up fitting. So all this, I hope, has given you an understanding and also a basic introduction towards how data can be simulated and fitted using a software like MATLAB. Thank you very much.